All right, our next theorem is due to Lindstrom. Here's a very nice theorem. Right, so suppose I have a n plus 1 subsets of sets of size n. Then there exist subsets I and j of 1 up to n plus 1 such that these two are not both empty, so at least one of them is non-empty and their intersection is empty. And when you take a union of these people, they have the same union, right? So you have a n plus 1 subsets from n set. You can always find two distinct indices I and j such that the unions are same. Oh wait, yeah. All right. So how do we prove it? This proof is due to Lindstrom in 1970s. Again, we use linear algebra here, right? So let vi, the vi1 up to vin. Now in Rn, so vij is 1 or 0, right? So if it's 1 if j is in AI and 0 otherwise. Okay. Now we have n plus 1 vectors. What does that mean? That means they must be linearly dependent. So there exists a non-trivial linear combination right? By non-trivial, I mean some coefficients are non-zero. So let I to be the indices where alpha I is positive and j be the indices where alpha I is negative. Alright, so I intersection j is empty and I union j is non-empty. And you can easily see that for when you add this thing together, then this is what you get. Now let's compare the row, right? If you look at the row representing some number, k, let's say, then that row is non-zero if and only if it occurs in the union. So this means that union of ai is equal to union of aj. So how simple is that? It's very simple. And there's a combinatorial proof which could be slightly more complicated. One can prove it by using Hall's theorem. Now I will show you different variations. Again, due to Lindstrom. And this wasn't, I don't know whether there's any proof without using linear algebra. So instead of n plus 1 sets, now we have n plus 2 sets. So these are subsets of n. Then there exist subsets I, j of 1 up to n plus 2 such that I intersection j is empty, I union j is non-empty, and the union of ai in I is equal, so it's the same union and same intersections. How do we prove that? We do this almost the same proof, almost, okay, except we're gonna make some variations. Now let vi be the vector, but I'm gonna fix last coordinate to be 1. So this is a vector in n-dimensional vector space. All right, why does it help me? Now, so v1, v2, vn plus 2 are vectors in Rn plus 1, so they are linearly dependent, so there exists a non-trivial linear combination. Again, let's use same notation. So now again, take the same set. So if alpha I is positive, I put it into I, and if it's negative, I put it into J. And then it's easy to see that the union of AI is equal to union of AJ, right? That's easy. But how do we see the intersection part, right? So now what we know is that sum of alpha I vi, where I is in I, is equal to sum of alpha j minus alpha j vj, and sum of alpha I is equal to sum of minus alpha j. Right. So what does this mean? This implies that whenever, right, so we're adding these two coefficients, and it turns out that there's some, right, these are like, these coefficients were like positive numbers, and we are adding them together and they are equal, right? So when do we add all of them? When you look at the, right, when I look at the intersections, okay, I mean, what would be the best way? There are many ways. Okay, so let me give you the easier way. Okay, so what is that? So E is this vector 1, 1, 1, 1, 1. Okay, if I subtract that, you're gonna have a same equation, right? So I can combine these two, I get this. That means these are the complement, right? Now, how do we make these two to be equal? Because that's when you have a union of this complement equal, right? But that is same as by De Morgan's law. That means intersection of these things is equal. All right. So that's the proof. Of course, you could make a different proof, but anyway, that's the proof. So we use linear algebra to say that if you have too many vectors in a small subspace, then they are linearly dependent, and that can be used to prove that there's a collection of distinct sets satisfying certain conditions.